Okay, Year 12. We're going to have a further look at logic gates and Boolean logic. So far we have looked at two different types. We've looked at Boolean algebra in that last HSC question I gave you that had the things that was like cross and circles and dots and pluses by themselves and lines above things. That's Boolean algebra. Okay. We also had a look at truth tables. Okay, so these ones where you put the zeros and the ones and said it was true, and then you did every instance of it and said it was false, blah, 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 blah. That's one way to represent Boolean. Oh, I was going to do it right. That's one way to represent Boolean logic. This is another way to represent Boolean logic. We're going to have a look at another way really here, which is circuits. But before I do, I wanted to go back and just reaffirm everything that we have done so far. So these are our different types of logic gates. Okay, you should be pretty familiar with them. When we're looking at circuits, you can actually represent Boolean algebra in a diagram, okay? And to compose said diagram, you need to use the logic gate pictures, okay? And so you need to be familiar with, this is an AND gate, it has two inputs, it has a thing like that and an output. This is a NAND gate. It looks exactly the same as an AND except it has that. This is a NOR gate. It looks exactly the same as an OR but it has this. This is an XOR gate. It looks exactly the same as an OR but it has that, and so on and so forth. This is a NOT gate. You can only have one input into a NOT gate in comparison to everything else. One input, one output. Okay, so an AND gate. I think I confused you a little bit before with the shoes and the jackets, and I think I might have said something incorrect, so I'll reaffirm it. An AND logic gate, you need to have true and true to come out with a true. You need shoes and a jacket, and you must have both. You can't have neither. Okay, so if I had 0 here and 0 here going in as my inputs, it is always going to come out with a false, okay, because it is an AND gate. This is how I represent AND with two inputs in a diagram that I'm going to use in my circuits. Can you stop? This is how I represent AND logic in a truth table with two inputs, so obviously A and B, and there's going to be an output. If I wanted to represent AND logic with Boolean algebra, I do so with this dot in the middle, and you'll remember that from that last HSC question. So it is A dot B. The only way to get an AND gate to come out with true is have both of my inputs being true. NAND. Easiest way to remember NAND is that it is an opposite. And when I have this A and B, I must have the line on top of it. That's how I represent a NAND gate in Boolean algebra. This is how I draw a NAND gate, this one here. It is simply the opposite of an AND gate. I've put the AND gate logic table down the bottom here. Where the AND gate has a 0, that must have a 1. Okay, where the AND gate has a 1, this must have a 0. So NAND is the opposite of AND, not AND, the opposite. Okay, so the only thing that comes out true with an AND gate is if you have both of them. Okay, that is the only thing that comes true with an AND gate. So with a NAND gate, anything but that is going in true. So 1 there, 0 there, that works. 0 there, 1 down here, that works. 0 here, 0 here, that works. That'll come out with a true. It's again, these two inputs going in here, they go through this gate. What output do I have? Okay, and it's just in order to work out NAND, you go with and then find the opposite. So neither shoes nor a jacket can have neither of them. Because if you remember in the AND gate, I had to have both of them. I couldn't have neither. So if I had to have both of them, the opposite is can have neither. OR gate, same thing again, and I represent it with the plus sign here. I'm not going to go through the truth table. You have to have one or one of these, okay? So if I have both of them, it'll work. If I have one of them, it'll work. If I have one of them there, that will still go through that logic gate. Can't have 0, 0. That will come out as a false. So neither shoes or a jacket can have both. So I've got one there, that works. I've got one there, that works. I've got one there, or I could pick that one there, that one works. This is my symbol. That is my Boolean algebra. This is my truth table. Cool, my NOR. NOR's easy. Just put my line on top. Sorry, I couldn't do that on the PowerPoint. So that's my NOR thing. This is my symbol. NOR is the opposite of OR. So all I've done with my OR table, that's an OR, that fits for an OR. So NOR is the opposite, put zeros there, okay, and go, okay, the only one that fits is not OR. So if I've got neither of them, that's not OR, so that's going to come out with a truth on that end. That's the only circumstance. Neither shoes or a jacket, but you can have none of them. That's the only one you can have, none of them. XOR is really easy, and you guys know this. Again, I didn't draw this symbol here because it wasn't in there. Your Boolean, sorry, that was really dodgy. That's what the symbol looks like. I couldn't just draw it in small view. XOR is exclusively OR, so I can have 1, 0 there. That'll come out with a 1. I can't have 1, 1 because then that's not exclusively OR, and I can't have nothing because you have to have either shoes or a jacket. You can't have both. It's exclusively OR. You need to know how to draw the truth table, what the symbol looks like, and you need to also know the Boolean algebra bit, so this bit here. Okay, not's really easy. The only important one to remember, so not A would be like that. The only important one to really remember is that not can only have one input. Okay, what not only has one input going there. Okay, it will only come out false if something is not occurring. So if there's a 0 going in there, that's always going to come out with a 1. As soon as that has a 1, that has a 0. Okay, so the other way to represent Boolean logic or logic gates, besides truth tables, is using circuit diagrams. You will have to be able to construct a truth table from a circuit diagram and construct a circuit diagram from a truth table. So we were doing truth tables from logic, or from words that we get given, like the sound car alarm, and from that Boolean algebra thing, from that last HSC question last lesson. Now we need to go back and go, okay, that's fine. I can make a truth table from those. Now I have to make a truth table from a diagram. Here's a really pretty version of a circuit diagram. Yours won't be this easy. We have 2 switches. What makes the light bulb turn on? Well, if I have a 0 going in here and a 0 going in here, hold on, what's my gate? Oh my gosh, it's an OR gate. So that's obviously not going to be turning on, okay? And I have a 1 going through here and a 0 going here. It's an OR gate again. Oh my God, so that's going to be turning on. It's a 0, 1 in here, 1's going in here, 0's going in through here. Obviously that's going to be turned on. 1, 1, obviously that's going to be turned on. So from that diagram, you will have to construct this. This seems really easy, and it is really easy because I've given you a really pretty circuit, okay? What I need you guys to do for me is going to be a really quick activity. Here's a circuit. I've done some really great mods on it here, and I've changed the logic gate. What I want you guys to do is to jump on to class. So underneath this video, I will also attach to this, above this video, a quick homework thing that I need you guys to do. In that Google Doc that I've made for you, I've already got this logic gate. I need you to please construct the truth table from it. It'll take you 2 seconds, and some of you will go, this is a waste of my time. If you are said person, on the next page of that Google Doc is an example of a HSC question. You have till Monday. I want you to do the truth table for this, then I want you to have a look at that HSC question and see if you can answer it. And that's it, guys. That is circuit diagrams.